Before we get going, this lesson, similar to our last one, I want you to download the actual sheet that goes with it so that you can fill it in as opposed to taking notes from scratch. It'll just save you a lot of time and a lot of pain. So anyway, jumping into our topic for today, measuring correlation. Last lesson, we took a look at correlation and regression, and we saw that correlation was, do you see a pattern and how good is that pattern? Actually, you know what? That's not true. We didn't look at how good the pattern was. We just tried to see if there was a pattern. And then regression was kind of to describe the path the pattern was taking. Today's lesson on measuring correlation is specifically to talk about, is the actual correlation good? How good of a path can we make out of the dots that we see? So in this title slide, we have a couple of things here. We've got our positive correlation, which uh, most people will equate with the fact that they're going upwards. It's got a positive slope, and negative correlation as being just a negative slope in it. That's not exactly accurate, but we'll talk more about that in just a moment. So the coefficient of correlation, which we're going to call an R value, it tells us how much of a trend there is between the two variables. The more extreme it is, whether it's positive or negative, the more extreme is going to tell us that the pattern is really, really good and really, really clear to see. Anything around 0 is going to be, I don't really see any pattern in the points. They're just random dots all over the place. And then somewhere in between, we have our weak or moderate or perfect correlations. Now, in the real world, perfect correlations are almost non-existent unless they're things that are mathematically true. For instance, if I'm trying to correlate the amount of money I make with the amount of money in my bank account, usually those are pretty close to exacts. If I put $1,000 in, I now have $1,000 more than I had before. That's a perfect correlation. But most real things like, your height versus your weight, even if they're strong, they're not perfect. So rather than try to try and name them based on the number, and this is what a lot of students have trouble with when it comes to mathematics class, we're going to actually associate a number with a description. So it's the description we're going to have. We want to put a number to it. There's really not much we do in this lesson as far as calculations go. We kind of describe things and then figure out what that means as far as the numeric values go. Okay, I'm going to jump over to the next slide, which kind of goes through the different words that we're going to use. I did leave moderate off here. Moderate is basically the one in the middle. So actually, I should go back here. You've got the numbers off the table there. Hopefully you just fill them in. Basically, it's just saying between 0 and 1, the first third is weak, the second third is moderate, the third third, that's what I wanted to try and say, is strong. So up to 33% or 0.33, up to 67% or 0.67, and then to 1. So the real definition of positive versus negative correlations isn't so much to do with the slope, although it works out coincidentally to mean or to be the same thing, positive or negative. Although a very steep slope doesn't mean it's very positive, and a shallow slope means it's very negative. All it tells you is the direction, up or down. And a positive correlation means that as one variable gets larger, the other variable tends to also get larger. So conversely, a negative correlation means that as one number goes up, the other number tends to go down, and it doesn't matter which is which. So for instance, I could say that as the number of hours I work increases, the numbers of hours I spend watching TV decreases. Work goes up, TV goes down. Or as work goes down, TV goes up. But they do the opposite thing to each other. That's really what makes a negative correlation, and it is kind of what gives it the negative slope. It just doesn't tell us how steep that slope's going to be. No correlation is best described by the graph right in the middle at the bottom there. A correlation value of approximately 0. Basically, you see a bunch of dots and there's virtually no pattern. You could not figure out where to draw a line of best fit on that if you tried. Weak correlations, again, I'm going to go down to the the graph at the bottom, so the ones on opposite sides of the center. Now, this particular one uses the terms low and high. We're going to use the terms weak and strong. Same difference. Um, a weak correlation means that you can see that the pattern's either going upwards or downwards, but you would have a lot of trouble drawing a line of best fit on. And you would find that if you drew one and your friend drew one, they may not be the same. Now, as we move towards strong or high positive correlations, that's basically saying that the pattern is so obvious that pretty much everyone who tries is going to get the same line of best fit, give or take a little wee bit. Perfect means that you can't possibly screw up the line of best fit. The pattern is so blatant. And I think if you look at the perfects on the far left and the far right, I don't know how you could do a line of best fit that didn't work on those. They're just too ideal. So again, we're not going to come up with the numbers, we're not going to determine numbers and then describe them. We're going to use the descriptions to try and figure out what the numbers should be. And this is really a little bit of a guessing game. I'll be completely honest. It's very hard to look at a graph and determine whether it's weak or moderate or strong and exactly what the R value is based on it. The good news is Excel or other spreadsheets do that just fine for us. The next thing we're going to look at is something called the coefficient of determination. It's an R squared. This is actually the coefficient of correlation squared, which pretty much means that if the coefficient of correlation went between -1 and 1, its squared value goes between 0 and 1. And this is the one that actually is used a fair bit more to describe how close two things are related. And you'll remember in the last lesson, I showed you a bunch of nonlinear regressions done in Excel for our data set. And I said that they were like 2% better than each other or something like that. And that's determined by Excel's R squared values. Now, I will point out that Excel and most other spreadsheets actually use a capital R instead of a lower r. It's one of the few cases in math where upper and lower seem to be interchanged. But for our purposes, we're just using lowercase r, but be aware that positive R squared means the same thing. Now, it actually has a little bit more tangible definition or interpretation than the coefficient of correlation, although it is by no means perfect. So don't take this as literal exactness. This is just kind of a way to think about it. So I'm going to look at these elephants. Now, I'm not sure if you're aware of this, but elephants tend to be about the same shape regardless of their size. Like if I think about a baby is like 1/3 head and 2/3 body. They have huge melons. And as adults get older, that becomes about 1/7. So baby people and adult people have very different proportions. Similarly, going from one adult to the next, you may have drastically different proportions. Knowing that someone is 5'8" does not tell me anything about their weight. They could weigh 60 pounds, hopefully not. They could weigh 400 pounds, again, probably hopefully not. But they can have a drastically different variation in weights. Whereas elephants, if you've ever watched a herd of elephants, they're all about the same shape. There's not a lot of difference between the shape of one elephant to the next. You don't see a fat elephant or a skinny elephant or, a tall, lanky elephant or one that's got like long, gangly legs or anything like that, or one with huge head. Like they all look about the same. They're very, very similar in shape and not necessarily size, but in shape. So I don't know if this is true or not. I'm making this number up, but we're going to say that the coefficient of correlation between elephants' heights and weights is 0.8. That is a strong positive correlation. Strong because it's a 0.8 value and anything above 0.67 is considered strong. And positive because as weight goes up, height goes up and vice versa. Now, if that's true, then we would have a coefficient of determination of 0.64. Now, what that does as far as the way we interpret it goes is that 0.64 is 64%, and then we would say that 64% of the elephant's weight is due to their change of height. So as they get larger, their weight will increase, and 64% of their weight increase will be attributed to their height change. The other 36% could be to a number of other factors, Some elephants might get more food than others. So there may be some that are slightly fatter or slightly thinner. Um, some might be sick. Some might have more access to water than others. Some might have slightly different genetics. There's a whole bunch of other factors that could be there. But what we're saying is a significant part of an elephant's weight is determined solely by its height. And then a little bit other stuff is determined by everything else. Whereas for human beings, it's very likely that it's a much lower number, both R and R squared, because a lot of a person's weight has less to do with their height than it has to do with their exercise level, their genetics, their eating habits, and so on. So there's a lot of other major factors for a person's weights versus its height than there is for an elephant's. Now, if you want to calculate R and R squared, there's the equation for R squared. And much like our line of best fit equation that we saw, I'm going to show it to you. We're not going to actually use it. We're not going to be calculating anything with it. But we could, and this is what Excel uses to calculate the R squared value. Now, the equation for R is obviously just going to be the square root of that. The only thing is, when we do that, we don't know whether R, because I should point out, Excel gives us an R squared value. It doesn't give us an R value. There's a good reason for that. When it gives us an R squared value, we don't know if the R is positive or negative from the equation, but we can tell whether it's positive or negative just by looking at the graph and saying, is the line going uphill or downhill? If it's uphill, it's positive. If it's downhill, it's negative. We get its magnitude from taking the square root, but we get its sign by looking at the actual correlation. The reason Excel does not do R's and only does R squareds is because the R value, the sign on it, positive or negative, really only makes sense if you're doing linear regression, if you're doing a line of best fit. If it's quadratic, the R squared value means the same thing. The R value is a lot harder to determine since a quadratic is either going to be positive then negative or negative and then positive. So we only do R squared values for nonlinear regressions. And I'll just show you here, if you do a line of best fit in Excel, and I should point out Google Sheets is very similar, so a slightly different place, looks a little different, but the idea is there, is that when you're making the line of best fit, you can actually click on these two boxes there. One of them says display the equation on the chart, so that gives you your regression. And the other one says display the R squared value on the chart. And that gives you your correlation, or more specifically, your coefficient of determination, but it tells you how strong the correlation is. Okay, we're going to get an opportunity to try that in a few questions or a few things later, but for now, we're going to leave it there, and I'm going to point out that there's some homework questions you can try to try and actually see if you understand how this stuff works. Until next time, have fun.